Good afternoon. Welcome back to the last session of the third day. I am uh, Najmul Hasan from Maulana Azad National University, the coordinator of this workshop, and I'll be talking to you methods in science. So, certain things probably would be a repeat of what has been said, but I think it's important because I say it the way I want to, and repeating it always helps to drive a point in better. But I'll be also covering things which have not been done by others. So, methods of science, right? So, doing science, doing research is something very typical of or very individualistic about humans. Though they are, so what is science? What is science? Science is from the Latin word scientia, meaning knowledge. It's a systematic enterprise that builds and organizes knowledge in the form of testable explanations and predictions about the universe. This is what Wikipedia says. And Academy Press Dictionary of Science and Technology defines it as the systematic observations of natural events and conditions in order to discover facts about them and to formulate laws and basic principles based on these facts. So there are certain things which are common in both, and we'll come to that. Both say that it is a way of building on knowledge, right? Working towards building knowledge, and it's a systematic way of doing it. It's an organized way to build knowledge, right? And this is what Richard Feynman, who was mentioned in one of the earlier lectures on the first day, he says about science. He says religion is a culture of faith, science is a culture of doubt. So what he means is, in science, whatever you do, whatever is being done, you always should you should try to doubt it. You should see and check whether you are right or wrong. You always keep questioning whether the results which we have got, however important and obvious they may seem, one has to keep checking whether it is true or would it fail somewhere. So it's a culture of doubt. And that's why science, as it progresses, it keeps changing. You cannot ever doubt in a religion. Religion, you have to accept it on faith and continue. You cannot question the premises of religion because if you do that, then the whole system fails. While in science, it grows by doubting it. At each stage, you doubt it and you build on over that. And this becomes very essential. And we have seen this in the past. See, there was a time when people thought that Earth was the center of the universe and everything went around us. And it was something very obvious. It, it agreed with common sense, it agreed with what appeared to be obviously right. This is something which even Professor Tandon spoke about in the morning. Things which we think are obviously correct may not be correct. So for a very long time, and even now when we see the sun is rising in the east and setting in the west, and it appears that that's what it is. But then, when the heliocentric theories came and people realized that it was the earth which spins from west to east, and hence you see the sun rising and setting. And so now, when we see that, we can very well imagine that we are standing on a spherical globe and which is spinning on its axis and also going around the sun, and hence we see the sunrise and sunset. So if a person doesn't doubt the premises and things, then they would be stuck at that and go on. And this thing has happened time and again. very obvious things have been questioned, which led to new scientific theories, new streams of knowledge, and so on. And they've become very essential and the crux of scientific discovery and research. Another example before I move on is the Euclid's axioms. If you have a straight line and a point outside it, you can draw one and only one line which can pass through that point and which is parallel to this, right? But then there were people who tried to question the nature of space and said that what if there was the space was not flat in Euclidean like we believe it to be, but you do the same thing on a sphere or on a hyperbolic surface, and then you see that instead of having a single line passing through another and parallel to it, you can find infinitely many lines which are parallel to each other and passing through a point. For example, the longitudes on a sphere on Earth's globe, they are all parallel uh, lines, but they all pass through the north pole point and the south pole point. So you have a point there, and you have infinitely many lines parallel to each other passing through this point. And this leads to spherical geometry, it led to hyperbolic geometry, and so on and so forth, which become very essential for the growth of science and mathematics. So, what are scientific methods? Uh, you have observations, you observe a phenomena, and you make a guess. You try to say that this is happening because this is probably what. Like, for example, you see the sun rise in the east and set in the west, and you do that the next day and the day after that, and so on, and you say that, oh, the sun is moving around the earth. So you have an observation, and then you set a hypothesis, which is a guess. And then you analyze this hypothesis in a rational, objective way, in a skeptical way. You question your hypothesis, and if your rationality and your objective way of arguing uh, still uh, explains that hypothesis well, lays within that hypothesis, then it becomes a theory. And once the theory is accepted as a theory, you try to verify this theory by other observations, by experiments, and right. So this theory has to be verified. There has to be a repeatability. So in science, it's essential that your verification has to be there, and then you predict. So once you get more and more confident about your theory, you say that this theory is right, and hence this should happen. And then you predict, and when observations stick to predictions, then you get even more confident, and the theories become laws, or they get accepted as very powerful theories and become the streamline or the backbone uh, of everything you do in that area and specific area. But if the predictions fail, then you rethink over the whole thing, you reanalyze, and you change your theory, and you try to explain uh, in the new paradigm what it is. One very important aspect of scientific method is falsification. This was discussed by Professor Prajit Basu as well as Professor Singh. So, in scientific theories, falsification is essential. If a theory cannot be falsified, then it is not scientific. If you have to take a theory as a dogma, a thing which cannot be refuted, uh, then it is not a scientific theory. For example, if I there's a beautiful analogy which Carl Sagan in his book gives. He says, suppose I tell you that there is this room, there is a dragon here, and and I say there is a dragon. You come into the room and you see nothing there, and then you see, oh, I don't see anything there. So you say, no, no, the dragon is there, but you can't see it. So then you use infrared to detect the heat which it throws. And you say, no, 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 it doesn't throw. This dragon is a good one. It doesn't uh, radiate heat, so you will not see it. Then you put chalk powder on the floor and you say, I want to see the footsteps of the dragon there. And you don't find anything there. And then you say, no, 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 this dragon is basically hovering there. So that dragon, whether if you cannot prove it is there or you cannot disprove it is there, then what is the big idea of having a theory of that kind? So scientific theory is either you should be able to it should be falsifiable. You should have experiments with which you should be able to show it is wrong. And if those experiments are they don't succeed, then your theory is right. But falsification is a very essential aspect in a scientific theory. This concept of falsification can never happen in a religion, right? You never start off with the premise that demons or gods they don't exist. You cannot do that. It's not done. But in scientific theory, you can try to falsify it and proceed and see whether that theory stands up to your test of falsification or not. And one another very important aspect of scientific theories are the Occam's razor. What this essentially says is a theory which is simple is the best theory. If your theory is very complicated, if you have many, you say this observations which I have, it is happening thus because this is such and such a thing is happening, this is there, and if it's a very complicated thing, then it's not a beautiful scientific theory. Also, scientific theory has to be simple. And you see all theories which are powerful, which have withstood uh, long eras of time, they are very simple theories at the philosophical level, at the basic level. You take the Newton's laws, or you take a theory of relativity, or you take the Mendel's theories. They are all very simple at the basics. Otherwise, it's not a beautiful scientific theory, and then uh, you can't go too far with it because you have to use a lot of axioms which are sitting at its base to prove anything, and the whole thing becomes very cumbersome. So coming back to our main thing, research in science. So we have looked at what science was, and now what is research? Research is a process of systematically obtaining and confirming new and reliable knowledge, right? So there are two keywords which are very important here. This research should give out knowledge which is new and reliable, right? You have to depend on what you derive out of it. Otherwise, the research, uh, the results which you get have not much of meaning. And often we require something new to come out of your research and theory. Or there are times where you prove the same things which you have known earlier, but in a more simple, more beautiful, more elegant way. So even that plays a role. So the reliability of what you prove is very important. And remember, it's a systematic approach of thing, right? So the research is the process of searching for explanation of events, phenomena, and finding the cause why it happens, what, how, and why things occur. In research, the process is planned and conducted to make information generated credible, right? So, see, there are different ways of obtaining knowledge. If I uh, get revelation, suddenly I'm sitting and I get an insight, and the whole thing becomes clear. then it is not research. Research is when you are trying to find answer to a specific problem and then you work towards it to get it. So if I'm sitting under a tree and meditating and suddenly I get insight into something, a revelation, some then that is not research. Research is a is conducted. It has to be planned to generate this credible knowledge. Then research is creative, and research is as it's circular. You start off with the observations, you set up a hypothesis, you test the hypothesis, you predict certain things, and you it throws out new questions and it generates new questions and then you work on it and it goes on. So the scientific method of research goes this way. You have you have observations and you set up hypotheses, then you try to predict and certain phenomena, and if your predictions are wrong, then you go back to the hypothesis and try to make changes to it. If not, then you continue. It gives you new theories and insight, and then it opens up new questions, and then again you work towards, you see whether it fits into your hypothesis or not, and so on. And in each case, either you are going positively or you have some falsified fact which leads you back to the theory to refine it and come to a better one. Sorry, in this diagram, certain words which were given are missing, but this is the circular nature which I was talking about. So the research process is cyclic. How do you start off? You identify a research problem, you specify a problem, you justify why you want to study it, and suggesting the need to study it for the audience, right? So we are living in times, there was a time when scientists lived in ebony towers. They had funds, they had resources, and they could do research on whatever things which fascinated them. But today we are living in times where the public is very much aware about the public funding which goes in, and you have to justify to your audience why you are doing certain research. So you have to justify. You can't say that I want to study galaxies because they are beautiful objects. I want to study collisions of galaxies, or I want to study issues related to diabetes because I am interested in it. You have to say that I'm studying problems of diabetes because I would find a cure and which would help so many people. The population in our society, so many of them have diabetes, and which diabetes leads to other ailments. It leads to mortality issues, so on. So you have to justify it, and hence this becomes very important in identifying a research problem. Once you have done that, you do review of literature. You locate various resources for the data, uh, uh, resources in the sense of how would you collect data and uh, right. So review what kind of work has been done, how much has been done, what are the open questions in that, and so on. So after a complete good review of literature, you specify a purpose for the research. You have found out what, so you had identified some area which you wanted to work in. Looking at review, you decide what is the relevant things which you can do in that area, and then you concretize your thoughts, specify a purpose for research, identify the purpose statement, narrow the purpose statement to research questions or hypotheses. Then comes the stage of collecting data, selecting individuals of study, obtaining permissions, gathering information. So they are, when you go into research in life sciences, research in various areas, there are a lot of ethical issues. So you have to get all these permissions whether you can get this data or not? What are the limitations? How are you going to gather it? And so on. And then you the analyzing and interpreting data, breaking down the data, representing the data, explaining the data. This is where you require statistics, you require statisticians. You have to find out from a statistician what kind of samples you need to connect. Suppose I want to study the effect of nicotine on lungs and lung cancer. So you have to decide a strategy of how you are going to collect your data, and how do you get a random sample. If I go to a cancer hospital and collect data from there, obviously it will give me a biased thing. It will show me that out of 100 people I have observed, 98 of them have actually cancer, because you are going there. But so if you want to say that what is the incidence of cancer in a community, in a specific region, then you have to take it from different quarters of life. Similarly, if you go to another place, say to a nursing home, and you pick up data from there, you will not find too many cases of cancer, but you will see, because specifically you are going to places where it's crowded by only a certain type of people who come with a specific area and interest, and so on. If I go to a football field and I'm looking for people who are interested in studying, I would find very few. I would find more people who are interested in football, right? So your sample has to be a random sample without any bias, and this is something very essential. This is what Professor Hargopal was saying. People say statistics is lies, damn lies, and statistics. Yeah, there are essays which are written, and people comment and say uh, lies, statistics doesn't lie, but liars use statistics. So this happens when you collect data in a biased way. When you start off with a preconceived notion that you want to prove a certain thing, and you collect data in not in a random manner, then obviously your results will be clouded, and you will prove, right. So that's not what research is. That's not how it has to be done. And then very important aspect, the last block on top, is reporting and evaluating research. So research done, and if your results are not reported, then it breaks the research cycle. So in the whole research process, reporting your uh, results is very important, in terms of publications, in terms of articles, in terms of theses, because this has to be reported. Otherwise, I have collected information, I have analyzed it, I have gained information, I have gained knowledge, and I keep it to myself. And there's no purpose of research of that kind. So you have to, reporting uh, is very essential. And when you are reporting, we had the talks in the morning, you have to decide the audience, the way it has to be reported. When you are reporting it for general audience in a newspaper, you do it in a different way. When you are doing it for experts in the peer-reviewed journals, you report it in a different way. So how you have to decide the audience, you have to structure the report, and writing the report, it has to be done in a sensitive way. Right, and once the report is out, it throws up new questions, and then it leads to new research problems, and the cycle continues. So the flow chart of research process through there are two processes where you can use quantitative and qualitative research. So you have this research process, you have the research problem, you do the review of literature, you define the research questions, then you make a decision whether it's the qualitative research or quantitative research. It could be a combination of both as well. And then you design on the basis of the decisions which you make. You have to design your research and design a methodology how you're going to proceed with it. In the quantitative design, you have to decide about the experimentation, you have to see correlations, you have to decide of the surveys, how are you going to collect your uh, data and so on. Then you have the qualitative design where you have grounded theories on which you build, look at the ethnography, the narrative of behind the whole thing, and you build the whole qualitative there. There you probably would not have to go and collect data and look at the correlations and so on. You are doing it. Yes, very often in mathematics or theoretical physics, we would do it this way. And then obviously there are some combined designs where you have mixed method, where you have people who are taking data, say for example, interdisciplinary one, biomathematics and biochemistry, right? So you have a mixed method where you are writing algorithms and you are testing it on people. You are making uh, MRIs, you are making CAT scans or various things. So you are doing mathematics, the fluid mechanics of the whole thing, and you look into the uh, uh, then you test it out on actual people and see whether it's right. So you have to then again pick up data and run your methods, techniques, and verify it. So once this is done, you have the sampling, how instrumental and protocols, data analysis, interpretation. It goes into all the three. And then you finally report it in terms of discussions, conclusions. You discuss the limitations of your work and then the future research. So very often when people defend their thesis, at the end of it, they say, what are they going to do further? How can their work get extended? And that shows the relevance of what they have done and would show that it doesn't end there, but it opens up new questions, which makes the whole thing much more richer. So coming to creativity in research, it provides the difference between satisfactory and outstanding research. So gather and use previously developed knowledge. These are some suggestions which I would like to make. When you are doing research, you have to find out what has been done earlier and you develop on that. Apply deductive logic to what you're thinking. Look at things in alternate ways. You don't just be dogmatic and keep doing it in the same way, because very often you would come to a dead end. So try to approach your problem in different ways. Question it and challenge the assumptions which you start off with. You keep questioning it. You try to uh, falsify it. You try to question and say that, are these assumptions wrong? What if the assumption itself is not correct? What will happen? Try to see patterns or relationships, and then be prepared to take risk. If you are too cautious and you want to proceed without taking risk, then you would not come out with something spectacular, something new. So do take risk, right? For example, uh, try to work on problems which are difficult and you don't see obvious results in that. Yeah, there are certain research problems which you know what the results would be. You just gather data, analyze it, and put it up, and you publish it. But it's boring. There's no creativity in it. So take risks. Try to work on issues which are difficult, which probably can lead to dead ends or problems. In research, it's very important to cultivate a tolerance for uncertainty. There are times when your work proceeds very rapidly and fast, and sometimes you lead to uh, lead into issues where you get stuck for it for longer times, and you suddenly are not sure where you are going, and you should not break down at that. You have to be tolerant. You have to have that in you to handle situations where you sometimes lead to issues which leading to this. Allow curiosity to grow and set. Sometimes you get stuck at a problem. It happens very often. So in such cases, I would advise leave that problems aside. Uh, there was some crosstalk. So set aside the problem for a while and come back to it. It very often happens in research that there are times when you feel really frustrated because you're not progressing. You think that, okay, I have done this, but the work is not progressing. Or you get stuck in a certain proof and you just can't come out of it. So best out of from my experience, I would say leave that problem aside for a while, give yourself a break, and then come back to it. So this very often helps, uh, really helps in, yeah. It's a good idea when you are doing research to write down your thoughts. This goes right from the beginning. When you start off with your research, you write down why you want to work in a specific area. Because when you are writing it down, it becomes clearer to you. Because if you are just keeping it in your mind, it could be a potpourri, a hodgepodge of thoughts which are there, which you think are logically and rationally arranged in your mind, but it is not often so. So when you write your thoughts down, then you see your sequence and your goals fine. Exchange ideas. It's very important that you talk to other people. This is what even Professor Tandon was speaking in the morning, and this is something which is lacking in our system. People are individually they are experts, and they just work on the problems on their own. They don't want to discuss with the person, the expert next door, and work on it. More in the morning, you discuss, you will give an example of Andre Weil and Fermat's theorem, that he had come to a dead end, and only when he opened up and discussed with his student, he could skirt around the issue and he could solve the an age-old problem, uh, the Fermat's last theorem. So it's very important to exchange ideas. Don't think that if you discuss your research problem with somebody else, they will steal away your work. It doesn't happen. Present your work in peer group, present in front of experts in the field, and it really helps. Uh, so this is out of experience which I have learned of studying in India and also working in Moscow and working in Russia. There you have large groups of people which move, work, interact, and they build with each other the ideas. So they are huge groups. If you see any publication, you will see that there are large groups of people who are working together, and it is very essential to do it. And when you present your work in your peer group, then as you are presenting, things become clearer to you, and you can get some input from your peer group and the experts in the field. So it's very important that you speak about your research problem, give frequent seminars, may it be in a small group, but keep doing it so that the problem becomes clearer and you can get inputs from others, and give some time to think. Okay, so collection of data uh, is important. How to collect data, how to analyze it, how to make sense of data, uh, identifying scales to measure the variables. These are all very important aspects. of the data which you have, and you have to go in an organized way uh, to get it. You have to identify the target population. You have to collect your data in a meaningful way, uh, knowing what the study objectives are, right? So you have to know what are the measurables you are looking for, and then you will be able to design your experiments or your data collection strategies better. See, for example, if the problem I want to study is, does smoking increase the risk of cancer? You identify what is the main aim of study. So suppose my main aim of study is to assess the risk of cancer associated with smoking. That's my primary objective. But you can also think of what are the secondary objectives which you can get out of it. Are there any races and gender disparities? So now I'm working towards the risk of cancer which goes with smoking. But when I am collecting data, and if I can also get a demographical access to that, and say also make a habit of other things in it, right? Then right in the beginning you can collect data in such a way that from your the data you have, you yes, you fulfill your primary objective, but you can many more issues which you can specify and say that, okay, yes, cancer get enhanced if a person does smoke, but if smoking is coupled with drinking, what happens? And the smoking in a certain section of society, among Indians, what is the incidence of cancer, and what is it when you are doing it in Europeans, or right? So then you can see whether there are other influences, effects of food or environment or other things which are also creating a role in that, right? So once you have primary objective, you can also have you can right away before you start off with collection of data think of the secondary objectives and things too. So study design, a careful advanced plan of data collection and the analytic approach is needed to answer the questions under the investigation in a systematic way. And the basic elements of study design are selecting an appropriate sample size, selecting methods of sampling, data collection, and analysis appropriate to the study's objectives. Like I said, reduce the bias due to the preconceptions or personal bias. Very often, when we start off with research, we have a preconceived uh, answer to what we are going to work on, and we think that yes, this is what is going to happen, and this is what we are doing, and then you start collecting your data in a biased way to go and prove a specific point, right? So that is against the rules of good research, meaningful research. So yes, so this is very essential. And then coming to statistics, this is, you are doing. I always felt that statistics is very important for for many areas of research, especially when it is quantitative research. There are some people in the audience, some mathematicians and uh, probably some theoretical physicists or theoretical chemists. They would not want to use statistics, or they may not feel the importance of statistics. But for a larger section of people who are in the audience, I know that they do research where they have to use statistics, and it is becoming more and more important as time is progressing. Even very basic sciences, they say, like for astronomy or genetics, or they rely on a lot of data, and you need statistical grounds on which you have to specify the validity of your results. And I will not get into this descriptive and inferential statistics as we discussed earlier. So you have descriptive statistics or inferential statistics, and you go through this flowchart, where you have descriptive methods which have different tests, univariate tests, bivariate tests, multivariate. So if you have data which have multiple variables, you are trying to find variation in a single variable due to something, or relations between two variables or so, or multivariable ones. So if you variate, then you look at the shape of the distribution, you look at the measures of central distribution, the mean, median, mode. Look at the spread, you look at the standard deviation, uh, and kurtosis and other things, quartile deviations and so on, and see how is the data spread against the central mean. Uh, and then you get an idea of what is the relative position. For bivariate, you have correlations and regressions. For multivariate, you have the multiple regressions methods. In inferential measures, you have applied to means and to other statistics. You have basically two groups, t-test and dependent groups on t-test, and then you have the ANOVA, analysis of variance. So these things will be studied in detail by Professor Hargopal. Right. And the importance of statistics in a very simplistic way. Say, suppose I have ages in months of 60 patients in the data. I have some 71, 127, 65, 82, 140. You just look at this data and it doesn't mean anything, right? But when you organize it in a proper way and you make a statistical inference, you make a histogram out of it, then you find out what it means. You run some statistical tests, you find out what is the mean, and you say 90.4. So you find out what is the average of it, sum of it divided by the number of elements, and you say, okay. Then standard error gives you how good is your measure of mean which you are getting. So if your standard error is small, then you realize that everything is clumping near the mean, and mean is a good indication of the data. And but if the standard error is large, then you can say that the data is spreading. So the mean value which you are getting is not indicative of the data you have, right? So similarly, median, uh, the most frequently occurring things, more and so on. And you right, so simple test, what is the minimum of it, what is the maximum, and and then drawing histogram, it is doing box plots, right? So statistics give you a way understanding. Otherwise, you just have scattered numbers from which you cannot make any sense of see patterns in it. Yeah, so I have mentioned this. I'll skip through this, and what I actually want to discuss with you also, that some open source softwares where you can do some statistical tests. I will give an introduction to and R and um, Python. Right, so statistical inferences too. Obviously, if you are studying a certain subject, it is good to study each and every individual to get an understanding into the whole thing. But very often it is not possible to do that, because you cannot, if you are trying to see the trend and see which party is going to come to power, you cannot individually go and check up each and every person in a population. If you want to find out the effect of uh, having excess of coffee on on an individual. You can't shake up every person living in a city or in a country and find out how much do they consume, what, and so on, right? So it's impossible. So you pick up samples and you study the samples, and there are these various tests which tell you whether the sample is a good representative of the population mean or not, right? So the sample collection has to be unbiased, and the sample should be large enough to tell you that the results which you are getting there uh, uh, does tell you about the population and so on, right? So this happens in all fields. Suppose I want to study all the galaxies in the universe. I can't study each and every one and tabulate and say how many are ellipticals, how many are spirals, how many. I have to pick up samples and study and make some statistical studies and say that so many appear to be spirals or ellipticals or in this region of space, this is what it appears. At different epochs in time, this is what it is. So you cannot study the whole population. So you pick up small samples, study them, and using these very sophisticated statistical techniques, make an estimate of whether your sample is a good representation of your population or not. So methods of sampling, you have simple random samples, you have systematic sampling and stratified sampling, right? So uh, like we all know a simple random sample is a subset of the statistical population in which each member of the subset has an equal probability of being chosen. There is no bias when you are collecting it. So if you have a population made up of all these different kinds of people who are uh, shown here with different colors, the chance of picking up an individual from the green region and picking up from the orange or from the blue, it should be equal. The probability should be same. Then it becomes a random sample. Systematic sampling is a type of probability sampling method in which sample members from a larger population were selected according to a random starting point and in a fixed periodic interval. Right? So systematically you pick up sample points in an organized way. Then stratified samples, you distribute them into different groups. The population, you know that they can identify into different groups, different ethnic groups, say the Asians, the Europeans, the Croatians, and so on. And then you know that they are made up of different genetic material. And then you pick up, or similarly, uh, you have these kind of strata in say botany. You have uh, different kinds of roots, uh, and you break them into different strata, and when you are doing sampling from these stratified, from each one you are picking up a stratified random sample and do it. So parameters and statistics, what is the difference? Parameter, any statistical characteristic of a population. For example, population mean, population median, population standard deviation. These are parameters. Parameters describe the distribution of a population. Parameters are fixed and usually unknown. A statistic, any statistical characteristic of a sample, for example, sample mean, sample median, sample standard deviation. These are some examples of statistics. Statistics. Not statistics, but statistic. But there are many, so hence I'm writing the statistics. Statistic describes the distribution of population. The value of a statistics is known and it varies for different samples. And they are used, these statistics are used to make inference on the population, on the influence on the parameters, right? So that is the essential difference between a parameter and the statistic. So statistic is used to understand what the parameters are from a population. Null hypothesis, this has been done by Professor Hargopal. You have null hypothesis and an alternative hypothesis. You set up levels of significance at which you want to accept these hypotheses. Then you have various statistical test statistics like t-tests, f-tests, chi-square tests, and so on. And you find out the probability values, p-values, confidence intervals, and so on. and describe the results and statistics in an understandable way. So just in a very broad way, a t-test is used for testing the mean of population against the standard or comparing the means of two populations. If you do not know the population standard deviations and when you have a limited sample, when you have sample size less than 30. A z-test is used for testing the mean of a population versus a standard or comparing the means of two populations with large n greater than or larger than 30 samples, whether you know the population standard deviation or not, right? And an F-test is used to compare two population variances. The samples can be of any size, and it is based on the ANOVA. So my suggestions are when you embark on research, decide the area you wish to work in, be true to what interests you, and identify your strengths and weaknesses. Explore what has been done by others at national and international level. Do not reinvent the wheel unnecessarily, right? Don't do something which has already been done unless you are going to do it in a more elegant or beautiful way. Understand your field. This qualifies you to make reasonable hypotheses about fundamental advances in the field. Choose the topic of research in which you want, which could be tackled in the time allotted. Do not strive to solve all problems in the field. Look for small advances in your field. Yeah. So this is a very important aspect which was being discussed in the morning too. When how do you decide the topic of research, and when you can't hear me? Yeah, so it's very important that you know the time allotted for that specific research. Whether the project which you have written is for 3 months, whether it's for a year, whether it's for 5 years, you have to know what's the time allotted, time allocated for that, and how much you can do, what results you can get in that time. This is very important at all levels when you are defining problems for our research scholars. Suppose I define the Riemannian hypothesis as the problem for my mathematics research scholar, something which has withstood for hundreds of years. It's an absurd thing for me to expect that it would be solved by anybody, however bright that person may be in that specific time. So there are times when uh, uh, research supervisors go wrong by allocating a problem which cannot be done in time, or it can the same mistake can be done by uh, even uh, profession researchers where they write a project and they promise too much. They say we are going to do this and this and this and this, and your project is only for a year. You cannot do all those things. So it's very important to know what is the thing you are tackling and whether the time allotted is sufficient or not. And keep looking at small advances, and these small advances lead to critical developments, right? So set small goals and keep advancing them. Last point which I want to make is prepare to report results even if hypothesis fail. You start off with a preconceived notion that you have set out to prove a certain thing, and your research, all the years of work would give you opposite results. Don't be shy to report that, right? False hypotheses are also advances in science. Failed hypotheses should also be used to make suggestions for future decisions. In fact, all big theories which have come out, they have come from false hypotheses. For example, Kepler, his whole life, he had certain preconceived notions why planets are moving in a specific way. He never thought that these planets are going around the sun in elliptical orbits. He had theories of harmony of the spheres. He had the five beautiful, perfect structures you have in uh, mathematics is what is defining their path. But his 17 years of research or even more led to something absolutely opposite to what he was thinking of. And he reported that people he it was very easy for him to slightly manipulate uh, the observations of Tycho Brahe to show that the planets are going around the sun in circular orbits rather than elliptical. Because if you look at the eccentricities of the planets which go around the sun, they are almost close to zero. They're almost circular. But though he believed that circle is a perfect path and nature follows perfect uh, paths. But his results, when it showed that it was not a circle, but it was a small deviation from circle, he reported that, and that was what made his theories so powerful and important. So, with this, I come to this last slide for this presentation. Uh, this is what Firebind writes in his excellent book, which is called Against Methods. He says science is essentially anarchic experience. Theoretical anarchism is more humanitarian and more likely to encourage progress than law and order alternatives. He says the idea of a method that contains firm, unchanging, and absolutely binding principles for conducting research meets considerable difficulties when confronted with results of history of science. There is not a single rule, however plausible and however firmly grounded in epistemology, that is not violated at some time or the other. Such violations are not accidental, insufficient knowledge, nor result of inattention, but are necessary for progress. Liberal practices in science is absolutely necessary for a growth of knowledge, right? So with this, uh, I'll say what he's trying to say. He's saying that it is very important to question and go against well-established, accepted laws of science because that's necessary in the progress of science. And all very highly established things which were always accepted as true were questioned, and only then science could progress. So you have to go against the methods to get new results, and that's the essence of methods of science. So this continues. In prehistoric times, people wondered where did everything come from? Why was nature how it was? And the quest continues, and we still are sitting with our highly developed scientific tools and still wondering how it all came about. So with this, I end this presentation, and I'll stop for questions. And if not, then I will go to the second part where I will hint to you uh, uh, some open source softwares which can be used to do analysis, right? So I will request the participants to ask questions and give comments. Are people there? Is anybody out there, or am I talking to myself on a screen? So thank you and thank yous and enlightened talk and so on. Uh, Very informative. Okay, thanks for all this. I really genuinely hope that you liked it. Uh, and I can understand that having 4 sessions constantly is difficult for you to sit and listen. But yes, and the last lecture is always a tough thing to follow. But yeah, so if there is nothing more, then I will take this opportunity. There are 15 minutes left, and I will just tell you what this R is and what Python is, and give some very basic things in it, so that you can and try to show how easy it is to actually download it and do your analysis. Okay, so what is R? R is a free software environment for statistical computing and graphics. You can do a lot of very sophisticated statistical computing using R. And the beauty of the whole thing is it is absolutely free. Okay, it's a free software. Free because you don't have to pay for it, and free because you can redistribute it. You can give it freely around. Okay. It compiles and runs on a wide variety of platforms. It runs on a variety of Unix platforms. It runs on Linux. It runs on Windows. It runs on Apple system, Mac OS. R is a GNU project, which is similar to a language which was called S, which was developed in Bell Laboratories, which is now AT&T and Lucent Technologies by John Chambers and colleagues. So R can be considered as a different implementation of S. There are some important differences, but much code written in for S runs unaltered on R. Let's not bother much about this because many of us have not used S, but we will be using R. So R provides a variety of statistical and graphical techniques. It does linear, nonlinear modeling. It does the classical statistical test. It does time series analysis, classification, clustering, and the list goes on. And R, like I said, is an open source software. It is absolutely free. How do we get R? How do we install it? Answer is Google search. Uh, you basically you just open your browser. So I'll show you how simple the whole thing is. You open your browser and can you see now? Can you see the screen? Can you see my browser? Yeah, you can see now. Right, so you just go and say R installation and you'll see R installation, all these, yeah, R installation and administration, CCRAN R project, R 4.02 for Windows, and here it is. R download for Windows. It shows how many megabytes, 64 version, or yeah. So you have to see what is your operating system, and you say you click for download R, and it downloads an exe file, and you save it and you run it, and it's there. Okay. If you are in Linux, you can again do the same thing. You go into that. You can say R installation in Ubuntu, or specifically in Debian or in whatever, and you go there and you have all instructions. Ubuntu at 16.04 or Ubuntu 18.04, and you have the source file, which you very often have to blow it up, untar it, run a dot configure and dot install. Yeah, you make file dot configure dot install. So they are all steps which are given there, which show you how to do it. Okay, so installing is very simple, and here it is. Now that I have installed it on this Windows, I'm doing it on Windows for demonstration because many people use Windows. Uh, Very often, an icon of this kind gets created, which shows R, and when I double click it, it opens up the R console. So R can be run through this from the line mode, or nowadays there are a lot of graphical user interfaces which can also be used, or you can run it through Jupyter Notebook. What it means, I'll come to it. So R Studio and all are more user. You have a graphical user interface, and by clicking of buttons, something similar to what Professor Hargopal showed with SPSS. So SPSS is no doubt a good software, but it is a proprietary software and it's an expensive one, very expensive. And I wouldn't advise anybody to use a pirated one and work on it. If your institute or you can afford it, fine. But R is, let me tell you, as powerful as that, and it is absolutely free. But yes, you have to go through a little bit of training to use it, and sometimes things which you do are not very obvious initially, but as time progresses, things become fine. So, for example, uh, you want to assign a value to a variable. Uh, what is generally done is you have x less than in a line, and I assign some value, say 8. So I'm assigning a value x to it. So when I say x, it gives you the value, right? I can say y is, I'm assigning a value, say 12, and when I say y, it gives me y's value. Uh, R can be used as a calculator, simple calculator, where you have x plus y, it gives you x was 8, y was this, and it works. So similar to this left assignment, there is this right assignment too, which works, which sometimes you can use for in specific things, where now I'm using a right assignment, and suppose I'm storing it in a variable called a. And now when I ask for a variable, I get what it is. And there are many things which you can do here. A to the power of 34, and you get what the answer is. So a, the double star notation works. Similarly, a cap 6, this also works. This is a into a 6 times, right? So it works this way. And you can do a lot of computation, this 4, 5, 6, 7 to the power of 45, and you are getting your answer 4.82369 e to the power of 164. You can set your display settings in such a way that it gives you the whole number if you wish, right? Acha, by the way, the usual assignment operator can also be used. For example, I can say uh, D is equal to 7. Yeah, I was using the left assignment, and even this works, and this absolutely does the same thing. So you don't have to use the cryptic way of right and left assignment. Uh, Even this has come into R now. Right, so I can define into A, uh, say, make it a vector, and I say A colon 5. And when if I say A, so A is a variable which is a vector which is saving 1, 2, 3, 4, 5, the whole of it. Okay. And if I say length of A, it will tell me what the length. They are 5, 1 to 5, and hence it's giving what the length is. And so as you get more and more used to it, you can see what it is. Now, if I say A colon and I say 2 in square brackets, uh, I get the value 2, and what it means is it is giving the second entry of the thing. Okay. And it is right. So if I had say a vector which was say B, which was not 1 2 3 4, but it was uh, say 45 to 50, and I had said B bracket the third element of B, it would give me, yes, my B is actually 45, 46, 47, 48, 50, and I'm asking for the third element, which is 47. Hence, it is showing what it is. Okay, and interestingly, if I use a negative thing, they say, if I say -4, and what it gives me is it will delete the fourth entry and give you the vector B in which you are saying delete the fourth element in that. Okay, so this way you can define things, and as you proceed further, you'll see how in a very efficient way you can keep using. And similarly, you can say define a matrix. I can define a matrix, and I say it is a uh, say 3 by 3 matrix I want to draw. So I say entries are from say 1 to 9, and it is a 3 comma 3 matrix. Okay, and this is what it gives, and it is following the convention of Fortran, where it gives the columns. You have a vector which we have created 1 to 9, and we are putting them in a matrix. So it's putting 1 2 3 in the column, then 4 6 5 and 7 8 9. This is what Fortran does, and what is done in C, it reads row wise rather than column wise. So even that is possible. So in that case, we can define this matrix, and I say by row equal to true, and when I do it, then it's putting 1 to 9 column wise, row wise, 1 2 3 first rows, 4 5 6 and 7 8 9. So you can make a matrix with the entries which whatever you need. It needn't be in this ordered way, and do it. And you notice the up key and down key makes you go to the things which you have been doing earlier. Okay, so another thing which you can do is there are certain data frames. We can save things in data frames. See, for example, I define a data frame called n equal to where is my cursor? Yeah, I'm defining n as column C235. I am defining S so the second, there's an extra here, column with true, true, true. And suppose I have uh, an S, which is basically column with, say, AA, BB, and CC. Okay, so my A is 1, 2, 3, my B is true, false, true, and uh, my S is true, false, and true. Okay, so I can define a data frame, which is, I define it this way, data dot frame n comma s comma b. Okay, and when I see what this data frame is, I get one which has integers, the second one which has some string, and B has logical operators. Right? So data frames makes it easy for you to have a table in which you can have not only integers, not only floats, but you can have a mixture of so on. Right? So similarly, there are certain inbuilt data frames, built-in data frames in C. For example, if there's something called motor cars, I'll just call this data frame, and this is a predefined data frame which is there in the memory. It is giving a list of cars with different entries on that, how many MPs, cylinders, so on and so forth. And then when we want to do some kind of statistical analysis, say, on this kind of data, I can do all kinds of things. I can say, for simplicity, I'll I'll come and I say require graphics, and I take pairs of from the data frame from where motor cars, comma main equal to this, which gives you the title, whatever you write here, and then the gap. And what it has done is done the pair plots of each one. MPG against cylinders, this display versus H horsepower, drag versus, right. So it is done all those plots, pairwise plots, right. So they're just very simple commands which you can use to do it and have your statistics running. Okay. So obviously R cannot be taught in a day or so, but what I want to show is you can download it and you can install it and run it. And one very interesting, important thing of R is the help. If you don't know a certain thing, the help is very powerful. The command is you can say help, and you say, for example, uh, uh, plot, and I run it. Right. Sorry, I help, and I say plot, and I run, and it opens up uh, internet, and it shows you uh, what is plot, generic XY plot, scatter functions, right? And you can go to click that and it tells you the description, how it is used, what are the variables, what are the options, and then you have some examples which shows um, all these examples, right? So help is very powerful. The community help of R is very powerful, and you can do that. Okay, I think we have gone beyond 5 o'clock, so I should not get down to uh, Python. Otherwise, I wanted to show you a little bit of Python too. Uh, some other time, maybe in the feedback session or so, I can run a small demo of Python and do it. Uh, if you are interested, I can do it now, but I can understand many of you may be already tired. There is a question here. Is there any software or app for R in Android version? I don't run it on your phone. Your phone computing facilities are not sufficient, and you cannot run it on your phone. Yeah. So run it on a laptop. Uh, buy a simple machine, install Linux on it, which is free, and you can run it. Similarly, Python is a free software, and again, uh, just take a few moments from you and Google search and you say installing Python and you get it, and then install say Python. Python is a programming language also into GNU. It's an open source object-oriented programming language, and you can download it for free, install it on all operating systems, and run it. Then do various statistical tests in a very simple way and absolutely free of cost. So those who are interested, we can have many sessions on Python or R, but here I just wanted to show that you can do high-level statistical work using these things. Okay, so I will stop with this and thank you all for your patience and hearing me. If there are any questions, yeah, there's somebody said we are interested in Python classes. So now what we can do is, what I could suggest is we'll reduce, on the last day we have feedback session and we have test. So in the feedback session, we can reduce that feedback thing because generally people are not too vocal and it is basically a big uh, waste of time. So we can do a little bit of Python there, just a start, so that you can build on that. And later, I can show you we are building a repository of uh, Python tutorials and data analysis using Python. And we will give you links of that, which you are most welcome to use it and work on it. So with this, shall we end the session? We'll meet tomorrow at 10. Goodbye and thank you.